seats. We have our next talk. So we have Dafeng and Martin, who are going to give a lovely talk about the various compute challenges based on using RISC-V. And so take it away.
Hello everyone, I'm Danfeng, and today we are talking about all in RISC-V and RISC-V all in AI. And I myself is a student ambassador on AI software of DeepComputing. And so what do we do? We are making consumer electronics based on RISC-V chips. And actually, we built the world's first RISC-V laptop in 2021, which is based on our Winner D1 SoC. And after then, we are making a modular framework DIY laptop. So I think some of us maybe know about framework. It's self-installable and repairable and replaceable parts, which means every component of this laptop can be replaced and upgraded. And we made several members which is powered by x86, ARM, and RISC-V. For now, RISC-V is our first-class citizen. And so in 2025, we built our first modular framework RISC-V laptop. And it's 4 cores, 1.5 gigahertz. So after that, we faced some problems. So first is we do not know our target market, and we do not know people wants how much computer power people wants, and we have limited money, and we need launch our product on time. So we began to thinking, and we decided to all in AI, because at the time, almost most of the most powerful RISC-V SoCs is coupled with AI coprocessor or neural processor. So we think maybe it's time to all in AI. So there were 2 typical cases. The first one is the first chiplet solution. The SoC is introduced by Eastwing, and it has 8 cores and 2 gigahertz, 50 TOPS AI computing power. And it has a dedicated NPU, which is pretty similar to the NVDLA architecture. And it has a private toolchain to use computing power. So we can say we cannot use TensorFlow or PyTorch directly on this laptop, but we can run dedicated Llama, not the mainstream. So so this is the first case. The product is launched in October 2025. And we have another case, which is an instruction draft, which means we have a SoC made by SpaceMeet, and it has 2 clusters, 2.5 gigahertz, 8 cores, which is capable for RVA23 profile, and this for the regular CPU. And we have another two clusters is dedicated for the AI computing, and we have 10 and 25 bits vector length and a much powerful tensor processor, which can deliver 60 TOPS AI computing power. So that is much different compared to the NPU solution. And they deliver the execution provider for ONNX runtime. So it's capable to run ONNX runtime for all of the ONNX models. And they also have a llama.cpp, but it's also not on the mainstream. So we face too much problems. So NPU is neither designed for all different kind of models, nor customized RISC-V AI extension instructions, which means if we want to run AI models, maybe the model is formatted in Cafe or ONNX or GGUF. I don't know, but we want to run this model on this CPU. But NPU and the customized AI extension is not fit in these cases. So, and these companies, these semiconductors, they do not have enough money and enough time. So we decide to partner a new AI framework. So, we get in touch with Modular, which is founded by Chris Lerner, and it's IRVM based and MRR based, and they have a lot of money, and they are extremely open, and they have a very open developer community, and all of the compilers and AI software steps is open sourced. So and is plenty new and lies technical depth. So we decide to support module and max. These are modular open softwares. Adapt this software on RISC-V chips. Okay, I'll stop here and let Martin do the hard part.
All right, thank you, Danfeng. Great job. So deep computing is absolutely great at building hardware. They take your chip, they build a motherboard, they get your developer onboarded. You can run the thing. You can actually feel it's not vaporware. They are absolutely great at that. But AI has a problem that you have a chip, but that chip cannot run any model you want. Well, most of the time, like, vendor will give you something, and it sort of runs, sort of doesn't run, depends on what vendor gives you, and okay, fine. Like, we all experience that, right? So I used to work on test torrents, was until like a month ago I left, but I'm right now a community developer, and anyway, I'm familiar with the architecture, and TensorRT faces a lot of the same challenges as deep computing has been facing. Like, we have a chip, the chip is great. I have a lot of faith in the chip and how capable it is, but running actual workload on there is hard. So just as introduction, to what's happening. Anti-installer, like we call it 10.6 processor. It looks like this. It's a grid of cores. The brown part is compute, and the green part is the DDR memory. So it's a grid. Like you can do systolic things. Like your classic systolic array literature applies from like the 1980s and 90s. You can do matrix and matrix multiplications very efficiently, like this. Like you load one of the matrix on one row, or you load the other side of the other column. You broadcast them. You send them around. That gives you matrix multiplication. But with RISC-V cores, you can do something more fun. You don't have to be brilliant and design every data flow pattern into your chip. You can kind of just, hey, I run software. I am RISC-V. I can control how that thing flows. So what do? You figure out, hey, you can load the matrix into one of the rows, do a what's called a ring reduce, and that's how you get general matrix vector multiplication. That's what language models care. But 10.6 cores are not really cores. There are 5 cores inside. You get 2 data movement processor that moves data in and out. And you get a unpacker, matrix and vector units, and a packer. The reason they did that was because hardware type casting, you don't need to spend cycles on dequantization, requantization. You just have hardware do that. You know what? This is and you write 3 kernels. That's hard. You're asking a developer to say, hey, write 1 piece of code is already hard enough. You have to write 3. And one of those have to run 3 threads at the same time. That's pretty hard, right? All right. How? How does that work? If you actually write actual low-level code, this is what you get. So you have something in it. You enter a loop, that's your core compute loop. You wait for data to be available. You make sure that your compute side have the register ready. You do the extra compute, and you commit that because you have 3 cores. You have to do synchronization, and then you have to prepare the output pipe and make it ready so you don't raise the output. The hardware is, recall that we have 3 cores that doesn't do compute themselves. They drive the engine. The math engine talks to their own register stuff, and so that's why you have to do synchronization. Different data get packed into register, stuff like that. So if you're familiar with hardware, which was I assume most of the people here are, it feels like a pipeline. So there's 3 cores. It controls 3 different hardware. It's unpack, math, and pack, right? And you have different registers. So effectively, you're doing a pipelining. And at any same time, your different cores are working on different workload and just pipeline. It's a pipeline. You feed data in, compute out. And yeah, so this is the acquire synchronization pattern across your 3 cores. So, but you can abuse this thing. It's double buffered, right? Like you're switching between register banks. So you can just, double buffer. So I'll just abuse the fact that registers will have the value be there. For any loop that's sufficiently large enough, the first two iterations, you can do some expensive compute to pre-compute and stick stuff in the register. And afterwards, it will be there as long as you don't override it. So yeah, that works. So yo dog, I heard you like data flow machines, so I put data flow machines inside your data flow machine. But back to vector code that we just saw, that thing was stateful. So if you look into the source code, this is what it looks like. There's constant register you can assign to, and it makes your computation kind of stateful. And it's very efficient. Like, trust me, it's super efficient. But it's super stateful. And therefore, if you try to init different stuff, and you call the wrong init function or you forgot one init function, worst case, your exponential function becomes logarithmic. Oops, sorry. Where am I? Sorry. And the chip is also super efficient. It does vector propagation, so like any GPUs, old school GPUs, but very, very space efficient manner. So, and for any block, like the if and else block are always executed, like GPUs. So it only affects vector code if you try to stick actual print functions or scalar computations between the vector if and vector elf, both get executed. And you have to be careful about divergence. So it goes deeper. Actually, inside the chip, there's a macro expander unit. So when you write vector code, the compiler will actually look for different instruction sequences that's repeating. It'll say, hey, this is a single macro that I can execute, and just tell the macro expander, hey, here's eight instructions. Please execute them while I'm doing looping logic. This gives you double the theoretical maximum instruction throughput without much hardware. Kind of like how DSPs does zero overhead looping. And this is why you kind of see weird patterns where you are incrementing the register value for some reason. That is why. That's because the compiler will generate instruction sequences that are identical for every loop, and they will be able to do the macro thing. So your dog, I hear you like dataflow machine, so I put your dataflow machine inside your dataflow machine inside your dataflow machine. Like, what's the architecture, right? But, these are hard problems. That is the current TensorFlow stack. The green part is GGML because I work on that and I love that thing. But we face the same computation problem. MPUs are inherently hard. These are efficient machines. These are machines with many tricks up their sleeves. They will squeeze every bit of efficiency out of the silicon. The hard problem is, how do you program the thing? Like, you cannot ask your developers to be a PhD in order to program your chip. That's just not viable. The solution is we need a better AI framework, whether it be deep computing. They think it's modular. I might think it's something else. But we need a better framework for computation and model of our computation. With that, thank you.
We've got time for maybe one or two questions. So someone want to raise, if anyone has any questions. Okay. Oh, there we go.
So if I understood correctly, you write the software and he does the hardware?
So we're kind of collaborating. DeepComputing is really good at doing hardware. I'm an HPC programmer at heart. I write code for different accelerators. We decided to make this talk because hardware is hard, software is also hard, and someone kind of has to be the first one to fix these problems.
Something I need to add that we DeepComputing make motherboard, but we also build AI software stack to help our customers to have a much more mature AI software stacks. Yes. So we DeepComputing also built softwares, especially on Linux kernel and AI software, AI infrastructure.
Anyone else?
Did I understand correctly that deep computing is building a machine or a piece of silicon where you have a mix of RBV implementations on the same board? One with 256-bit vector length execution, and one with 1024. That's going to be wild. That's going to be really cool.
So basically, you have to implement software using vector extension, which is vector length agnostic. Basically, you have to do so, but some engineers, they do not have this this kind of field. They build the software, use SIMD method. So, how to say? I think the community may upgrade the legacy works to build vector length agnostic software.
Thank you very much. That is all the time we have.